I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die.
All right, our speaker this evening is Dr. Charli Sakari, Assistant Professor of Physics and Astronomy at San Francisco State University. Charli earned her bachelor's degree in physics and astronomy at Whitman College in Washington State. She earned it with honors there. Then she earned her PhD as a Vanier Scholar at the University of Victoria in British Columbia, followed by postdoctoral work at the University of Washington. There at UW, Dr. Sakari developed her skill for giving popular astronomy talks with provocative titles, including, get this title, Radioactive Stars as Cosmic Clocks. I got a tentative promise from Dr. Sakari to present that someday. Evidently, cool titles are her strong suit, because tonight she is presenting Galactic Archaeology, Galaxy Assembly with Globular Star Clusters. Please welcome Dr. Charli Sakari.
Thank you all very much for having me today. So I'm very excited to have the opportunity to talk to you today. Thank you very much for inviting me. And I'm going to talk about the work that we are doing here at San Francisco State, specifically the work with galactic archaeology, and we'll talk more about what that means. But first, I'd just like to introduce my research group at San Francisco State. So here we are, most of us in a Zoom celebration that we had last December. And here we have our students. And so we have two that have now moved on to PhD programs. Jonathan Cabrera Garcia was a master's student here and is now at Notre Dame. And Ami Dabokemp was an undergraduate here and is currently at NYU. And then I have several master's students working with me, Ray Stanley, Hamza Khan, Jessica Agnos, and Dilpreet Kaur. And then two undergraduates, Donovan Evans and Alona Kosabakova. And so these are wonderful students who are doing great work, and I'm definitely going to feature their exciting work that they're doing today. So what we're going to be talking about this evening is I'm going to tell you about the general goals of galactic archaeology, which are to understand galaxy assembly, and we'll go into why that's important and why we want to do that. I work in particular with chemical abundances of stars and clusters, and so we'll talk about why chemical abundances are so useful, and we will talk about how we get those through observations. Then I'll go into more details about globular clusters and why they're important for understanding galaxy assembly. We'll talk about star clusters in the Milky Way, and then I'll give you just a little bit of a teaser about how we can actually go beyond the Milky Way to more distant galaxies, and we'll use M31 as an example of this. And then we're going to do a bit of a deeper dive into our chemical abundances, and we're going to focus on two specific elements, barium and europium. We'll talk about how we create barium and europium in the universe and what the information they give us. And then finally, we'll end with a little bit of discussion about our place in the universe. So to start with, we'll dive into our general goals of galactic archaeology, and the general goal of my research is similar to a lot of astronomers. It's to understand the universe. No small feat, right? But what I mean by that is, we sort of have this paradigm for how the universe forms, in the Big Bang. And we know that, somehow we form stars and galaxies, and then galaxy evolution proceeds until today. And really what we'd like to know is we'd like to understand how these first stars and galaxies form and how they evolve to what we see today. But sort of more than that, we'd like to understand the physics that are underlying our universe and that dictate this process. So that's our general goal, is understand the universe and the physics that underlie the universe. So there are a variety of ways that you can get at this question, and the technique that I use is often commonly referred to as galactic archaeology. So to understand this, we can, talk about terrestrial archaeology. That's archaeology on Earth. So archaeologists, we typically think of as digging up old objects and using those objects in their old state now to understand civilizations that occurred in the past and to understand the behavior and actions of those civilizations. So that's basically what we're doing in galactic archaeology, except instead of civilizations, we're studying galaxies, and instead of old objects, we have old stars. So we use the stars that are currently in the galaxies to infer something about the past histories of those galaxies. So for instance, if we look at a galaxy like this is the Andromeda galaxy, M31, we can look at the stars in that galaxy and ask questions like, where and when did those stars form? And how did they get to where they are now? We can then ask, is this galaxy like others? Is it unique or is it more commonplace? And ultimately, we can ask, are the properties of this galaxy consistent with the physics that we think underlies the universe? So a bit of a discussion about what that physics is. We kind of have a good idea of generally how galaxies form and generally what the universe is made of. So we know that the universe is made of dark energy, dark matter, and sort of normal matter. The dark energy and the dark matter you've probably heard a bit about. They comprise the bulk of the universe, and the normal matter that makes up stars and planets and people is a very small part of the universe. But if we, may run simulations, this is an example from a simulation, we can see that we predict that galaxies assemble from mergers of smaller dark matter halos. So you have these, dark matter clumps, and over time they merge together to make bigger clumps, and those are what we then know of as galaxies. And so that's sort of our general paradigm for how galaxies form, through these ongoing mergers of smaller galaxies. So we see a lot of evidence for that in the Milky Way, but there's a lot of open questions about the Milky Way in particular. So in particular, we might ask, when do these mergers happen? Did they happen early on when the Milky Way was very young, or are they ongoing and happening now? We can ask, what kinds of galaxies are coming in to build up our Milky Way? Are they, very low mass? Are they bigger ones? Are they major mergers? Things like that. And then ultimately, a really important question, is the Milky Way an unusual galaxy, or is it a more commonplace, typical one? And this is really important because the Milky Way is the galaxy we know best, obviously, because we live in the Milky Way. And we have lots of data about it. But realistically, if we want to understand galaxy assembly sort of, in a big picture, universal scale, we need to understand more galaxies than just the Milky Way. And so, the paradigm we have for galaxy assembly is kind of one like this. We see in this artist's impression, we have a large galaxy here that's sort of, has a smaller galaxy falling into it. And this is a process that we call accretion, is that the bigger galaxy is accreting that smaller galaxy and it's falling down into it. So that's our sort of rough paradigm for galaxy assembly. So that's what we're trying to do really with galactic archaeology, is we're trying to get at those details for galaxies, how they assemble. And the way that I approach this is by looking at the chemical abundances of stars. So the chemical composition. To understand why this is so cool, we have to think a bit about how stars form. So we know sort of roughly that stars form in these clouds of gas and dust. And so this is an example of a nebula that's showing, a star forming region. So we have these big clouds of gas and dust that are going to collapse down and form stars. Now, when we think, a star will form billions of years later, it may not be in that, anywhere near where it formed, because it'll move away from the other stars, it'll move away from the nebula. And so billions of years later, it's going to be far away from here. However, what will remain the same is that the star will retain the chemical signature of that nebula. So it forms from a cloud of dust and gas, and it will be made out of that same material for its lifetime. It has there are a few elements that change due to stellar evolution, but for the most part, the star retains the chemical signature of its birth environment. Even billions of years later, it's moved on, it still has the same chemical signature. Another key factor here is that the composition of this nebula depends on the stars that came before it. And so that means that the composition of a star depends on the stars that came before it. So you've probably heard the Carl Sagan quote, "We are star stuff." That's referring to the fact that the elements, for the most part, form in stars. So all of the elements that are present in this nebula and that will end up in its stars are the result of the stars that evolved and died before this nebula formed. So we can kind of understand that in this graphic here from NASA. So this is showing a star-forming nebula here. And we have then these two different cycles that are happening. So out of the star-forming nebula, we can create these protostars. And the protostars can either be, stars like the sun, or they could be more massive. And if there's, stars like the sun, they go through an evolutionary process where they become red giants and then planetary nebulae, and then they blow off their outer layers and become white dwarfs. Whereas massive stars have a different evolutionary process. They are massive stars. They then become red supergiants or other types of stars, and then they become supernovae and can end up as neutron stars or black holes. But a crucial part of this is that during the planetary nebula phase and during the supernova phase, the stars eject material. So in this case, they blow it off, and in this case, they explode, and that material can go back into a new star-forming nebula, and then new stars will be formed in that star-forming nebula that are enriched in the products of these stars. And so this is why we have a cycle, because stars form, they evolve, they produce new elements, and they deposit them into a new star-forming nebula. So over time, we have this effect where stars increasingly enrich what we call the interstellar medium. And so when we look at a star, we know that it's retaining that chemical signature of its birth environment. We know that that depends on the stars that came before it. And one last cool piece of this is that if we look at stars that form in dwarf galaxies, small mass dwarf galaxies versus massive galaxies, they actually have different chemical signatures. And we can kind of understand this by going back to this plot. So dwarf galaxies just have sort of fewer stars in them because they have lower mass, so there's just fewer stars. So that means that they won't go through as many cycles as a massive galaxy like the Milky Way. So they're going to have star-forming nebulas that get enriched differently. But this is particularly cool because it means that if we look at stars that formed 10 billion years ago, we can tell whether they formed in a massive galaxy or a low-mass galaxy. So now I want to go into a bit more detail about what we talk about when we mean chemistry of stars. So you've probably, or maybe you've seen this joke before. This is the astronomers' periodic table. So in astronomy, we have hydrogen, we have helium, and then everything else we call metals. And this is a historical thing. And, it kind of has some motivation to it. So like I said, the heaviest elements are formed in stars. In the Big Bang, we create hydrogen, we create helium, trace amounts of elements like lithium and beryllium, but everything else is formed in stars. So that's, part of why we call them metals, I guess. I will say things like Metalpoor or metallicity, and what I'm referring to is then kind of an overall abundance of these other things. But actually, I'm interested in more than just this rough description of metals. So here is a periodic table that is now color-coded by the different astrophysical sites that create these elements. And so, here we see hydrogen, and most of the helium is created in the Big Bang. Whereas, the blue and the green and the orange and the yellow, these are all created in stars. And we will go into much more detail about the periodic table in just a moment. But what is important is that each of these elements gives us information about the stars that have come before our star formed and the types of processes that happened there. So again, we'll come back to this in just a moment. So how do we actually, so I see a question. If the stars in the dwarf galaxies have different chemical structures than the stars in massive galaxies, does this extend to the age and size and color distribution of stars? So they don't really necessarily evolve differently. They just have, different amounts of these heavier elements. And most of them actually, stars are still mainly hydrogen and helium. And so the trace elements have very little effect on their evolution. Yeah. So I see there is no emptiness in the universe, or is it the dark matter? Yeah, so, dark matter and dark energy are, both kind of prevalent through the universe, as well as the baryonic matter. But really, we think of most of space as being the vacuum, which, has some properties to it as well. Yeah. But, other people could give whole talks about dark matter and dark energy, and they're certainly very fascinating. Yeah. All right, so now back to the chemical abundances of stars. So how do we actually get this information? How do we, for instance, know the iron abundance or the calcium abundance in a star? Well, we get that information from spectra. So to see that, we would look at a star, for instance, this one, and we would take the light and we would spread it out into a spectrum. So you have hopefully seen this album cover before. So in this album cover, we have white light that we put through a prism, and that makes a rainbow spectrum. And we don't typically use prisms in the type of spectra that I use, but the principle is the same. You take the light and you spread it out. And so if you were to sort of look at something like a light bulb, or, typically when we look at the sun through a prism like we would expect to see a rainbow spectrum. And so you might expect to see something like this. But actually, if you look at a star like the sun, and you're able to actually, look very carefully at the individual colors in the rainbow spectrum, you'll actually see something that looks like this. And this is the rainbow spectrum, but on top of it, there are these dark bands, and we call these absorption lines. And these are specific colors or energies where there is light missing. So light has been sort of removed. And so we can understand this by sort of thinking about what a star is. So here is a graphic that I have made that is very much not to scale, obviously. This is a huge telescope for one thing. But anyway, so if we had sort of just like a light bulb sitting in space, kind of a perfect thing that's radiating, and the light traveled to us, we may expect a rainbow spectrum. So that's kind of what we think. But that's not actually what's happening with a star. A star actually has an atmosphere. So the light that's coming from the center of the star where the fusion is happening, once it's able to make it out of the star, it has to travel through this more tenuous atmosphere. So similar to the Earth's atmosphere, but nothing that we could ever breathe or be in, because it's very hot, of course. And so when it travels through the atmosphere, it hits individual atoms that are there. And these atoms have electrons, and those electrons are then able to actually absorb specific energies of light. And so when we see these absorption lines, we actually know that they are caused by those specific atoms in the atmospheres of the star. So for instance, we can say, oh, this specific line is a calcium line, and this specific spectral line is a hydrogen line, and this specific one is a sodium line. And this allows us to determine that those elements are present in the atmospheres of the star, even though there's not very many of them compared to hydrogen. And in addition, the darker this line is, the more of that element is present in the atmosphere. So we can use the what we call the strengths of these lines to determine how much of these elements are in the atmospheres of these stars. And what we typically see, we don't typically look at spectra like this. We typically look at them like this. So this is a plot here. We have wavelength is on our x-axis. That's color. And so to demonstrate here, this would be, the purple end here would be very short wavelengths. The red end would be very long wavelengths. This plot that we're looking at is just a very small section in sort of this greenish yellow part here. So a very small section of that. And then this on the y-axis is what we say normalized flux. And so what that means is we've removed the rainbow spectrum. So if it was a perfect rainbow, it would be here at 1. And so we see all these dips down here are those dark lines that we're seeing in the other one. And if it was completely dark, it would be down at 0. And this is a spectrum of the sun in that very small chunk. And you can see there's a lot of absorption lines in here. And I've labeled some of them based on the element that created them. And so we have a bunch of iron lines here. Here's barium, silicon, zirconium, vanadium. So a lot of different elements that are present in the atmosphere of the sun. And what is particularly cool about this is, as I mentioned earlier, these elements each have different nucleosynthetic sites. So nucleosynthesis is the creation of the elements. So that means they each form in slightly different ways in different types of stars. So that's exactly what we saw in this periodic table here, that they form in different ways. And so each one of them is giving us different information about the stars that came before the sun or before whatever star we're looking at. All right, so that was our real crash course in sort of what we're doing, what the goals are, and how we do it. So now I want to jump into talking about globular clusters and their importance for galactic archaeology. So here is a Hubble Space Telescope image of a Milky Way globular cluster. This is the cluster M15. And you can see globular clusters are some of my favorite objects in the universe. They are beautiful. Even without the Hubble Space Telescope, they're beautiful. And we can see that a globular cluster is generally something that looks like a glob of stars, right? It's fairly centrally concentrated. There's a lot of stars there. And in the Milky Way, sort of all of the classical globular clusters are old. And by classical, I really mean obvious. And we'll talk about this in a moment. So in the Milky Way, they're all old. This is not necessarily the case in other galaxies. For instance, the Large Magellanic Cloud has some younger ones, for instance, but in the Milky Way, they're all old. In the Milky Way, they also tend to be different from another type of cluster, which is the open clusters. So here's another globular cluster. This is 47 Tuc, which is a southern hemisphere cluster. And again, we see this nice, centrally concentrated, lots of stars, really beautiful. And that's different from this kind, which is an open cluster. And, we're really creative with our names in astronomy. It's more open and diffuse, and you can see through it much better. There's many, many fewer stars in open clusters generally, and they tend to be younger. And in fact, they really have to be younger because they don't have as many stars, and so they're much easier to disrupt, in the gravity of the Milky Way, and with all the other things around it, the cluster can get destroyed much more easily. I've kind of set this up as a nice, obvious dichotomy where you have globular versus open, but there are actually a number of clusters that kind of fall between this paradigm. And that aren't obviously one or the other. And so here are some 3 images of some clusters that have been classified as globular clusters. And these are all in the Milky Way. Here's one that I guess you could maybe believe. Here's one that is less easy to believe. And here's one that you cannot even tell by eye that there's a cluster there. You can only tell it when you kind of plot the stars in a plot. And there's a lot of questions about, can these even be considered globular clusters? Are they really the same thing? Do they show the same chemical properties? Sometimes these things are younger or they have some other weird characteristics. This one in particular, Palomar 1, looks like it may have originated in a dwarf galaxy. So that was my first paper that I ever wrote, was about this particular cluster. And this is the subject of Ray Stanley's master's thesis. So she will be looking at 4 of these sort of unusual clusters. They're located sort of in the central regions of the galaxy. So they're additional factor of weirdness there. And so she'll be studying those and kind of answering these questions. Do they look like the normal globular clusters we expect? Or maybe did they seem to have originated in dwarf galaxies? So stay tuned for that. That will be exciting work. But I want to return to the composition of globular clusters because that's what I am most interested in, is the chemical compositions. And so I want to return to this timeline of the universe to think about how the chemistry of the universe evolves with time. So as I've mentioned, after the Big Bang, eventually we have this period of Big Bang nucleosynthesis where we create the first elements. And in that process, we have hydrogen, we have helium, we have trace amounts of lithium and beryllium, but we have no heavy elements like iron. And just for reference, when I say iron, I often write Fe because that's the symbol in the periodic table, but it is iron. So we have no heavy elements like iron in the early universe. All of those elements have to be created in stars. So we can only have them after the first stars form. And you may have learned in an astronomy class, for instance, that massive stars actually evolve faster than low mass stars. So massive stars, they have more mass, so they can be hotter at their centers, and they go through their material faster. So they evolve first. So after the first stars form, the first ones to die are the massive stars. And they're going to create iron, and then subsequent generations are going to make even more iron. And so sort of roughly we can say that the amount of iron in the universe is going to go up with time, starting at the point where the first massive stars have evolved and died. And what we see with the Milky Way globular clusters is that specifically with iron, they have a wide range of the amount of iron they have. And but many of them are what we call metalpoor or iron poor, which suggests that they are kind of from this region of the early galaxy, but shortly after the first stars have formed. We also know this because they're old as well. And another cool thing about globular clusters is that they kind of reside in the outskirts of the Milky Way, some of them. So here is an image from NASA that's kind of breaking down the components of the Milky Way. So here we have the galactic center in the center of the image, and then the bulge is kind of this part in the center that surrounds that. The disk is what we see here. The sun resides in the disk. This is where all of the current star formation is happening in our Milky Way. And this is where many of the stars that we see in the sky are in the disk. This is also where open clusters are because they're younger. So they've formed here in the disk. Globular clusters, however, many of them are in this extended spheroidal part of the galaxy that we call the halo. So this is, kind of suggesting that they may have formed in a disk, but they ended up in the halo later, or they formed during an early part of the galaxy's history before things were really settled down. But sort of our simulations that we run suggest that globular clusters form during periods of really intense star formation. And so this kind of is giving us a hint that globular clusters are probably probing the earliest star formation in the Milky Way. As well, we're going to talk about this a little bit. They're going to probe accretion to the Milky Way. So when those dwarf galaxies are coming in and building up the Milky Way, they're going to probe that as well. And one last cool feature of globular clusters is that their formation is rather mysterious. Star formation in general is not yet well understood, which is exciting, of course, because we have a lot of stuff to learn. But globular cluster formation is especially weird. So sort of naively, you would think if a globular cluster forms out of one giant molecular cloud, the same cloud of dust and gas, we would sort of naively expect all of the stars in the cluster to have the same chemical composition. We'd expect them to all have the same iron abundance, the same calcium abundance, the same, magnesium abundance. But in fact, that is not the case. All of the globular clusters in the Milky Way have variations in some of the lighter elements like sodium or oxygen, but there are some that are also especially peculiar. And one of these is the globular cluster M15. So M15 actually has a spread within the cluster of a type of element called the R process element. And we're going to come back to this in the next portion of this talk. But this is the subject of Jonathan Cabrera Garcia's master's thesis, which is characterizing this spread in M15. So this is particularly important because globular clusters, as I said, are sort of probing a really important part of the Milky Way's formation and assembly. And so if we really do want to understand as best we can how these clusters actually formed. So since we've kind of gone over a lot of different features of globular clusters, I thought it would be helpful to summarize them really quickly before we move on. So we talked about how globular clusters really trace these periods of intense star formation, because you need to have a lot of star formation happening to make these big, massive clusters. In the Milky Way, they particularly seem to trace these ancient star formation and accretion events. We know that most of them are old and metalpoor. And some indeed seem to have been accreted from dwarf galaxies. So they formed in these dwarf galaxies that are then building up the Milky Way. And on top of this, globular cluster formation itself is a bit mysterious. We don't totally understand it, but it's an important part of the puzzle. So I see, oh yeah, solar system planets aren't supposed to have the same composition. So that's a good point. The planet formation process has, some things that are different with the structure of the planets in particular and whether they're rocky or gaseous. But in general, they're the composition of Jupiter shouldn't be terribly different from the sun, for instance. But those things are a bit more understood than why two identical stars would have a different composition. Yeah. All right. So does the Milky Way have any nearby dwarf galaxies? Yes, the Milky Way does. We have a lot of nearby dwarf galaxies. So we have one, in fact, that we are currently accreting called the Sagittarius Dwarf Galaxy. And I'll go back to the artist's impression of that. It looks somewhat like this, where we can actually see the streams from that galaxy being currently accreted. And then we also have the Magellanic Clouds, our nearby dwarf galaxies that you can actually see with the naked eye in the southern hemisphere, although I have never seen them with the naked eye because it's always been too bright when I've been there. And we have lots of other ones. Some of them are, obvious dwarf galaxies. Others are much harder to see, when you look at them in images, because they look very similar to those sort of sparse clusters I was showing. But yes, there are many of them. Yeah. And some of those dwarf galaxies have their own globular clusters as well. Yeah. So one last sort of general cool thing that I want to talk about with globular clusters is that we can use them to do these kinds of studies to look at the chemistry of systems beyond the Milky Way to galaxies that are very far away. And I'm only going to talk about this briefly because that is a whole talk in of itself. But I just want to highlight this with the example of the Andromeda galaxy. So the Andromeda galaxy, or M31, Messier 31, is the largest, the nearest large spiral galaxy to the Milky Way. So it's our sort of, nearest neighbor that beyond the dwarf galaxies. That's a massive galaxy. And even though it's relatively close by on a universal scale, it's still really hard to observe its stars and globular clusters. So for instance, here is sort of a typical image of M31 that you might get with a sort of reasonably sized telescope. I think this is an amateur astronomer's image. And this is showing, here's the galaxy. And then these points here are some of its globular clusters. So they look, more or less like stars in this image. And to kind of understand why, we can look at Hubble Space Telescope images. So here again is a Milky Way globular cluster, the one M15 with the Hubble Space Telescope. And here is one in M31 with the Hubble Space Telescope. You can already see, like, this one is not a 3-color image, so it's not beautiful like this one, but you can already also see some differences. You can't see anything that's happening here in the center. The stars are too close together. They're not really separated. We can't see as many stars in the cluster. you lose a lot of information. But most importantly, these are not on the same scale at all. M31 is much further away, so the star cluster is much further away, and that makes it appear smaller on the sky. And if I try and put these on the same physical scale, it would look something like that. And in fact, PowerPoint wouldn't make it much smaller than this. So that's kind of what we have to deal with, right? It's much harder to get sort of the same information that we can get from this image out of an image like this. And so because of this, we have to get creative with how we observe these systems. So in the Milky Way, if we want to know more about a globular cluster, we can just look at these individual stars. And so we can if we want to take a spectrum, we have to put a spectrograph slit on our star, and we can get the spectra that we want for any star in the cluster, basically. If we want to look at this one, however, we have to observe the entire cluster. We have, an entire cluster fitting within the spectrograph slit. And this is a technique that's called integrated light spectroscopy. And this was really the bulk of my PhD research and my postdoctoral research as well, was in doing this in testing this out and doing this in M31 as well. So to understand the power of this, here's an even more distant galaxy. This is NGC 1407. It's an elliptical galaxy. And in the center here, we can't see any individual stars because they're all blurred together. But instead, we can see the individual globular clusters that are surrounding this galaxy. And there are thousands of them. And so this means that we could get integrated light spectra for these globular clusters and use that to sort of do the same sort of science that we're doing with individual stars in the Milky Way. And this, again, is really important for that question of, is the Milky Way unique? Is it unusual? And those sorts of questions, because we want to observe other types of galaxies as well. All right, so that was our crash course for globular clusters and their importance. Oh, so I see, why is there no new star formation in globular clusters, or is there? Wouldn't the massive stars in globular clusters die earlier and form material for new star formation? So globular clusters don't have gas anymore. So the massive stars, they did indeed die earlier and produce material, but for the most part, it was ejected from the cluster. And that was also quite a long time ago because they are billions of years old. And so there may have, some of them may have experienced some amount of ongoing star formation where they're kind of continually enriched. But for the most part, that's not what happened, because we see actually very little spread in iron in these clusters. And so that tells us that there was not a period of ongoing star formation. There is a little bit of additional bit here that I'm not talking about, which is the sodium and oxygen part of it actually tells us that there is something complicated going on as they form, possibly with some sort of self-enrichment. But whatever it is, it happened relatively quickly. And relatively quickly, the gas gets ejected and star formation stops. Yeah. All right, and so now I'd like to do this deeper dive into two elements. We'll talk about barium and europium, and then we'll talk about our place in the universe. So for these two elements, we'll return to our periodic table. And so one thing we can notice, just sort of casually looking at it, is that we see a color change roughly halfway through this, where we switch from, a blue-green color scheme to a yellow-orange color scheme, sort of roughly halfway through the periodic table. And this is, kind of because we have a difference in how these elements form. So in general, the lighter elements up to iron form through fusion, where we take, nuclei and we slam them together to make heavier elements. The heaviest elements in the periodic table, however, cannot form that way because it takes way too much energy to slam those nuclei together. Instead, they form through a different process, a process called neutron captures. And so to demonstrate what a neutron capture process is, I have an illustrative video here. And what this is going to show is we have a nucleus here that's made of so many protons in red and neutrons in blue. So neutrons have no charge, so they're able to just go into a nucleus and stick there. The complicated part of a neutron capture process is actually making those neutrons, so it can only happen in so many places. And how quickly the neutrons come in can happen in two ways. So we can either do it slowly, which is the S process, or rapidly, which is the R process. We're very creative with our names in astronomy. And this particular video is a rapid one, but it doesn't really matter. It's not going at a quick time scale. But what we see in this video is that we're going to add on more neutrons, and the neutron number is going to go up. However, this makes our nucleus unstable. And so what we see here is that at some point, the nucleus becomes too heavy, too unstable, and one of these neutrons goes through a decay into a proton. And we see when that happens, our proton number goes up. So the proton number is what defines what element we have. So for instance, we have nickel here because it's 28 protons, and then we create copper with 29 protons. So if we have enough of these sort of adding on neutrons and then decays, we can create heavier and heavier and heavier elements in this process. The specific elements that we create depend on how quickly we add on these neutrons relative to that decay timescale. And so if we return to this periodic table, I mentioned that these are identified based on the astrophysical sites, but realistically, we could actually call this orange is R process and yellow is S process, the rapid dumping of neutrons or the slow dumping of neutrons. And if we focus in on the two that I want to talk about, barium and europium, we see barium is primarily S process and europium is primarily R process. They do have a small component that is created in both processes, but for the most part, it's S versus R. And if we return then to the sites that the table had them identified, the S process is known to happen in low mass stars when they reach the end of their lifetimes. If you may have heard of it, it's called the asymptotic giant branch phase. Whereas the R process, one of the sites is thought to be merging neutron stars. I put this question mark here because that's still in debate as to whether it's the only site. Oh yes, and I see Hal is asking, what is the gray and gray thing? Green and gray thing. Yeah, one of them is, I believe, positron, and the other one I think is a photon, maybe. Yeah, that's a good question, Hal. One of our SF state students. Yes. So merging neutron stars are a candidate for how the R process happens. And I want to point out that neutron stars come from massive stars. They're the end result of a massive star's lifetime. And so we see that they come from the R process and the S process come from different types of stars. So massive stars create the R process, low mass stars create the S process. So if we think back to our timeline of the universe again, in the early universe, we have no barium or europium because none was created in Big Bang nucleosynthesis. The first massive stars evolve. They are able to create barium and europium in the R process. So the R process in the universe increases with time. As this then introduces questions already about neutron star mergers. Can they happen early enough in the universe, and are there enough of them to be able to explain all the R process? I'm not going to answer these questions, but they are definitely, because they're still open questions, but they are definitely important questions that we should ask about the R process. After enough time has gone by, lower mass stars can evolve to the asymptotic giant branch phase, and they will then create the S process, which produces barium, but very little europium. And so the amount of S process in the universe goes up. And so I want to focus in on the R process component here. And so, for me, the S process kind of messes things up because it gets in the way. It makes things more complicated. I would like to just study the R process. And so it would be nice if we could sort of look at this period of this snapshot of time before the lower mass stars had evolved, but after the R process had been produced. And so to do that, we want to look for stars that are sort of, in this range here, maybe. And so if we look at other elements that can help us to find stars from that phase. And so, for instance, remember that there was very little iron in the early universe, and then subsequent generations made more iron. So what this means is if we want to look for these stars in this region, we want to look for what we call metal-poor stars or iron-poor stars. And in fact, many of the globular clusters are in this category. And so just to remind you, metal-poor means all of the stars, all of the elements, are deficient, but we're going to use iron as a proxy for metallicity. So we're looking for iron-poor stars here. And the search for these metal-poor stars in particular is a goal of this collaboration that I'm a part of called the R Process Alliance. And so we want to understand R process nucleosynthesis and how this contributes to the buildup of the galaxy as well. And so one of our primary goals for this collaboration is to identify some of these metal-poor stars that are enhanced in our process elements. And so we have a survey, and the goal of this survey is to find more of these and use them to understand our process. So we have a couple steps to this. One is to identify candidate stars from large surveys. And I have several students who are working on this, which is why I'm mentioning it. So Dill's MS thesis in particular is characterizing metal-poor stars in apogee, so looking for some of these stars that are in a particular survey called apogee, whereas Ami and Donovan are both finding target stars from another survey called the Globular survey. So they are doing this excellent work to find these candidate stars that we can then study. If we want to actually get the information about the R process elements, we need to get those nice, beautiful spectra that I showed you, for instance, with the sun. And so to do that, we have to do more observations to characterize R process enhancement. And so here are some of the papers that the R Process Alliance has published in the past. And with some of them, we might even want to go back and get better data, better spectra to get even more information. And so that is, some of the students are also working with this higher quality, better data. So Hamza Khan is doing his MS thesis about a specific type of star called limited R stars, whereas Jessica Agnos is looking at another highly enhanced R process star. So they're doing their master's work on these spectra. Another thing we can do is we can look at how these stars are moving around the galaxy. And orbits are really important because they can identify these stars that formed in dwarf galaxies or may have been brought in. And this is what Alona Kosabakova is doing for her senior project, finding the orbits of some of these stars. So that was just sort of a crash course in what a lot of my students are doing with the R process. But I do want to return to M15 because, as I pointed out, it has this spread in the R process. And actually, most globular clusters are at least moderately enhanced in the R process. But M15 does have that star-to-star spread that former master student Jonathan Cabrera Garcia was looking at for his thesis. And so here is a figure that is from his upcoming paper that's looking at the amount of barium compared to iron relative to the amount of europium compared to iron in a bunch of different stars in M15. So most of these are from the literature. Jonathan has had 6 stars for his master's thesis, but he's going to have 63 for the paper that he's working on now. So that's a lot more. Previous observations have shown that whatever has happened to make this spread had to have happened as the cluster was forming. It can't have been like something that happened nearby and polluted the stars. And so Jonathan's paper will double the number of stars in this plot and increase the number of available elements that we have, and will give us a lot of information about where the R process enhanced stars are, spatially in the cluster. And so he's doing a lot of really good work with that. So yeah, stay tuned for that as well. All right, so we've now gone all the way through are focusing on 2 elements. And just last few minutes here. Oh, so yeah, question. When you say there was no europium, barium, iron in early universe, is this based on observation or modeling? If you can observe them, do you find them nearby? So that is based basically on our, models of the Big Bang. And there are observations that are sort of tracing, pristine environments. And yeah, so realistically, like the conditions of the early universe as we know them just it wasn't possible to create those heavy elements. Yeah, so in those models, you can only create hydrogen, helium, and trace amounts of the lighter elements, and then that kind of matches what we see with the observations. Yeah. All right, so now just in the last few minutes, I want to focus on our place in the universe and take a little bit of a segue because we've been talking, about galaxies, and I've talked a lot about the Milky Way and how the Milky Way fits in with the universe. But of course, we're here on Earth, and it may seem like these galaxies are far away and like we don't really have anything to do with them. But one of the things that I've been doing lately is working in a large international organization called Astronomers for Planet Earth. And so this was an organization that started at SF State actually in 2019 and then merged with an organization in Europe. And we have, over 750, I think it's over 1,000 now, members from 42 countries, 6 continents. We're growing all the time. And we are a group of astronomers who really want to bring our unique astronomical perspective and our knowledge of physics to the discussion of climate change. And in particular, I've already mentioned one of the things that one of the pieces of expertise we have, which is the formation of spectra. I talked about how stars have atmospheres and the interaction of light with atoms creates this absorption spectrum that allows us to determine the compositions of stars. Well, the same process happens on Earth, but the spectra, of course, look very different because the atoms and molecules that are present in the Earth's atmosphere are very different, but the principles are the same. And so we as astronomers have expertise in a lot of different things that are useful for this discussion of climate change, including this discussion of atmospheres and chemical abundances, Earth's connection with the sun, placing Earth in an astronomical context, exoplanets and the impossibility of traveling there, and physics of climate change and solutions, and much more. And so I just wanted to give this brief advertisement to Astronomers for Planet Earth. And if you're interested in learning more, you can visit our website. You can follow us on social media. We're on Twitter, Facebook, and Instagram. And I do want to highlight our fabulous videos on Vimeo and YouTube because Jessica Agnos, who I mentioned as doing her MS thesis in my group, has made several fantastic videos, including one, A Brave and Startling Truth, that features a poem by Maya Angelou that's read by Jessica's daughter, actually. And so, yes, please check those out if you're interested. So now to end, in conclusion, the chemical compositions of stars are useful for understanding where the stars formed and how galaxies have assembled over time. Globular clusters are a really important part of this puzzle because they trace periods of early intense star formation. Some have been accreted from dwarf galaxies, and they do allow us to study more distant galaxies. And our process elements can help us to answer some of these questions while also studying where our process nucleosynthesis happens. And then as well, astronomy does provide this unique perspective on climate change that we can use to educate the public and learn more. So with that, thank you very much, and I will take more questions.
Wow, Dr. Sakari, thank you. I must notice this is the first time in its 33-year history, I believe, that the Mt Tam Astronomy Program has featured an archaeologist as its speaker. Terrific. Yeah. And especially one so generous with giving us information and giving a claim to her grad students. Where's the tradition of principal investigators taking all the glory? You give the glory to your students. That's beautiful.
Well, if I could give more glory, Jessica Agnos has also made a video where she was Indiana Jones. She superimposed her face on him, as being an archaeologist.
Ah, very neat.
Yes.
Okay.
Yeah.
You might have noticed at the early in the chat, I invited folks, if they'd like, to just raise their hands via the reactions button at the bottom of the Zoom window if they would like to ask the questions themselves. But it looks like you've done such a good job of answering the questions as they'd appeared in the chat bar that maybe you have eliminated our curiosity here. That's impossible, but all right, let's see. Would you welcome questions via email if somebody does?
Yeah, sure.
Yeah, yes. Your email address is?
Oh yeah, I can put it in the chat. I think Stuart, did you have a question too? You're coming from Monterey Bay Aquarium.
No, I'm in the living room actually. Thank you very much for the presentation. I enjoyed it, though I did have some technical difficulties, so you may have answered my question. We, of course, have been hearing about the new super replacement for the Hubble, the James Webb, and so I was wondering if if you anticipate that telescope would give you wonderful new data, views, and also related to that, I guess I was wondering whether or not most of the information, the data that you use for your research comes from optical telescopes or the other kind of telescopes. Thank you.
Yeah, that's a great question. So I did mention the Hubble Space Telescope, which we have used a few times. It's not our primary telescope, though. And yeah, our future space telescopes will certainly be helpful, but they won't entirely replace Hubble, because one of the features of Hubble is its ability to look in the ultraviolet, and that will not be on James Webb. And so that's a feature that will be missing. But still, James Webb will definitely get great images of globular clusters, and we'll be able to go even further. Most of the observing that I do with spectra is ground-based and optical, although we do use the near infrared as well. So for instance, I talked about Ray Stanley's work with stars that are near the center of the galaxy. For those, they're covered in dust, or they're obscured by dust along the line of sight. And so we actually need to look in the infrared to be able to see them, because the infrared light can make it through the dust. But for the most part, it's telescopes in the optical. And I have used many different telescopes. In particular, I used Apache Point Observatory quite a lot when I was a postdoc at the University of Washington. That was the main observing that I did there. But I've used, telescopes at Kitt Peak or Mauna Kea or in Chile. Yeah, lots of different places.
Thank you for your question, Stuart. And of course, Dr. Sakari, thank you. I've got a series of folks to thank here. We'll save you for second to last. I want to thank our audience for showing up this evening, for putting up with another video in this long COVID night of in-person get-togethers. Thanks to the audience. Thanks to the supporters of the Mt Tam Astronomy Program and to Wonderfest. Thanks, of course, to Dr. Charli Sakari. And I want to say a fourth thank you here to the creator of the Mt Tam Astronomy Program. For 33 years, she has dedicated her good portion of her life to astronomy outreach and to enlarging our view of the cosmos and enriching it. That is Tinka Ross. So as we applaud, perhaps with silent American Sign Language applause, as we applaud Dr. Charli Sakari, please join me in thanking Tinka Ross, who's in our audience tonight. Thank you, Charli. Thank you, Tinka.
Thank you, Tinka. And Tucker.
All right.